There we go. Starting recording. So we're talking about homework 5 here. Hello, everybody, roomers and zoomers, and YouTubers, as it were. So then we pick up another predictor in section 2, which is whether the participants had training in pancakes or crepes. So you could leave this as a typical between group variable where 0 was one of the groups and 1 is the others. And so that would be what it looks like in this case. And so what I was doing here is trying to describe the difficulty, in my head at least, of keeping it this way, is that some of these terms are switches and some of them are variables, where some of the means then become linear combinations and some are not. So for instance, if I wanted to know what is the expected pancake outcome for someone who was trained in pancakes, under this coding scheme right here, where pancakes is the 0 for training and crepes is the 1 for training, the predicted pancake outcome for someone who was trained in pancakes would just be this DBP right here, because that's when the rest of this would drop out. 1 second. Whereas if you wanted to know what was the predicted pancake outcome for someone trained in crepes, you'd have to add these two together, because you'd get both of these are for the pancake outcome, but this one's for the reference group, this one is for the alternative group. So the idea of which is a variable and which is a switch started to make my head hurt. So this is the workaround that I did. I made 2 additional dummy codes where if they were trained in pancakes, it's a 1 and 0 otherwise. If they were trained in crepes, it's a 1 and 0 otherwise. So I've also seen a couple people do this as just a 4-category grouping variable, for instance, because you're basically just splitting out 4 different possibilities. So if you do this, then this is one cell of the design, the expected pancake outcome for someone trained in pancakes. This would be the expected crepe outcome for someone trained in pancakes, the expected pancake outcome for someone trained in crepes, and then crepe and crepe. So I like this way better because the means are given directly by the fixed effects. Any mean differences are just -1, 1 linear combinations. The one thing that I've helped several people troubleshoot so far, though, is directionality. So the questions, let me find an example of one of the questions here. For someone trained in crepes, for instance, enter the estimate for the within-person mean difference of pancakes versus crepes. So the ordering of what comes first for the versus, I tried to make it so that the outcome that should be better comes second, so that any mean difference or training would be a positive amount. And so sometimes it's pancakes versus crepes, and sometimes it's crepes versus pancakes, because it depends on the focus of the question as to which should be the preferable combination. So if you get the standard error correct, but your estimate is incorrect, odds are good you flipped it. So enter -1 times your answer and see if that works. And if that is the problem, then it just means that you assigned the 1 and the -1 backwards relative to what I had intended. Okay, does that answer your question? Okay, big nod, good, okay.
Lisa, can I ask a follow-up question? Because
Please.
This is what I was running into. So if you flip back to your other screen, I had originally set up 2 to be like that top, with the, underneath bullet 2.
This?
That's how I set up my code, and I ran into the same thing that you were just saying with directionality. And that's where I was getting at, one of the interaction terms should be the difference. And so I guess I'm confused as to why, the model would flip to a negative coefficient. Does that make sense?
So the direction of anything tied to this is going to be how crepe differs from pancake, how the 1 group differs from the 0 group, and sometimes that is backwards from what the question asked.
Oh, got it. Okay, that makes so much sense.
Yeah, so
I was like, why is this not working?
And I didn't mean to make it as crazy, but the idea is this is meant to represent a type of experimental design where it's congruent versus incongruent. I see that a lot in psychology, at least, and in cognitive types of studies. And so this is meant to sort of map onto that, what is the effect when there's congruent training and outcome? What's the effect when it's incongruent? And that's why I switched the direction of whether it's pancake versus crepe or crepe versus pancake, is because sometimes it's incongruent versus congruent. So.
Perfect. Okay, that makes so much sense. Thank you.
Yes, no problem. Who else wants to ask questions? on homework that is due tomorrow, not yesterday?
I can ask a quick question. I'm not sure how to articulate it quite yet, but for the section 3, it asks about the effects of experience on the outcomes.
Yes.
Can you talk a little bit about what those linear combinations would look like?
Yep. So at the end of section 3 here, you should end up with 4 different experience slopes, one for every possible combination. The idea is that the effect of experience should depend on what you were trained in, but it also depends on whether what you're making what you were trained in or not. So there's 4 slopes to the model, and what I did is just tack them on to each of these. Actually, let me make it correct, because we need to keep those in. So those are the means. Come on, here we go. Like that. And then add the slope to each, like that. So there's no main effect slope, and each of these directly is the slope of experience in that particular combination. And so if you want to know how the slope of experience differs across combinations, then those are estimate statements with -1s and 1s. Okay, does that help?
So then we don't have to make a separate training variable category, like with the 0, the 1. I think it's written in the instructions on the homework. We can continue with the same code that we used in section 2.
Yep, you can replace the 0s and 1 with one variable with 2 different variables if you put them in this capacity. Okay, big smile. That helps? Okay. There's like 18 ways you can set this up and get to the right answers. I'm just describing the way that I felt like was most useful, is to represent each combination with its own set, like this. And this is what I do for any type of design where it's a factorial type design, where you might have like 2 levels of one categorical factor and say 3 levels of another. If you don't have a fully crossed design where all 6 cells are possible, then this is the type of model that I would set up instead, is just to give a separate mean for each cell and then get whatever comparisons I want as linear combinations. So I do this in those sorts of settings, as well as in, smart designs, sequential, something, adaptive. They're clinical trials where halfway through you look at how people are doing and reassign them to a new condition if they suck. So it's like an adaptive randomization. I think that's the end of the SMART thing. So that type of design ends up with a lot of uncrossed cells, and so this is how I would set up the model for that type of design. Okay, what else? Question?
Yes, my question is referred to the example 5a that we covered last week.
Yes, I can get that out.
Page 8, please.
Okay,
Because
page 8.
I have a question. For section 1 and 2, I use the factor approach.
Mm-hmm.
And in order to get the F-test, I use the E-means part, but
You find page 8 here.
for section 3 is page 8.
Okay, getting there. So what happens when you have a 26-page handout?
In the
Come on.
F0C, page
Oh,
page
1, 2,
8.
3. F0C.
7.
Should be
Yeah.
page 7?
At the middle. Save. No.
This?
Scroll. The first.
This is 8.
The first part of code. Yes. Those -1, 1, and 0. Yeah, that
This.
part.
Okay.
Why? In that part, I know that you are using the dummy code approach to get these dependent variable groups. How can I know how to do this F-test? For example, if I'm using 4 groups, because in this case we are using 3 groups, but I do not know why you are using -1, 1, 0, comma, and then the same linear combination again.
Okay. So this linear combination is lumping together 2 of the possible pairwise differences across respondents. And in this model, the 3 respondents are kid, mom, and dad. So the coefficients go in the same order as the fixed effects are listed in the model. So
Okay.
like the -1 here refers to kid,
Exactly.
and the 1 here refers to mom.
Mhm.
So this is kid versus mom as one difference, and this is mom versus dad as
Yes.
another. And it doesn't actually matter which ones you list as long as you list 2, because the model would give you the third as a linear combination, so it doesn't matter. So this is a joint hypothesis test, basically what corresponds to, in repeated measures ANOVA, you would call this the omnibus effective condition, or whatever words you want to use for your repeated dimension. This is asking whether there are any mean differences across the 3 types of respondents.
So, if I would like to repeat this process with 4 groups, for example, I would need the
You ne-
same structure but 3 brackets.
If you had 4 groups, then you'd add another one in here like that.
And-
So you need as many
brackets.
places as you have fixed effects in the model.
Okay. I will try. Thank you.
And if it doesn't work, you may be off one, because it will yell at you if you don't have the right number of values for it to parse here.
Okay.
And how to do some of this in a factor setting, I'm less sure of. I just know that I was able to find it with the em means command without having to do much typing.
Okay.
So. Okay, what else? I do have office hours at 3:30, so you're welcome to come hang out. You can pop in or you can hang out and work. Email is also fine. If you are going to email me questions about this homework, though, please tell me how you set up your variables. That way I can look at your code in the context in which you intended it, because just seeing the model line is not going to necessarily tell me what you meant. And if you are using a factor variable approach in R, be careful. I have learned, thank you, Vladimir, that it changes the interpretation of the experience slopes against your will. He thought he was setting his model up one way, and R's like, nope. So once we figured that out, everything worked just fine. But trying to figure that out took a few minutes. So in R, you can look at the list of fixed effects, and you can tell from that usually how it's been parameterized. If you see experience sitting all by itself, and you intended it to be attached to a dummy code, then that will cause problems in how your results would be interpreted. Okay. Anything else on homework? Okay. Then I will remind everybody that they have until the end of finals week to get everything wrapped up. And that is like a lifetime away, right? It's like 2 whole weeks, 2.5 weeks. One way or another, it will all come together. As a reminder, on finals week, I am going to be in Zoom office hours during the regular time in which I would have been teaching. So to both classes, office hours from 12:30 to 4:30 Tuesday and Thursday of finals week. Your 6th homework is just about ready to go. It will be a path model, which we're going to be talking about today. Another thing that you would have gotten an email about is course evaluations. Did everyone get the university-sanctioned email about course evaluations? Yes. Course evaluations are used in all kinds of decisions about faculty, and I would like to have a strong response rate. So I would like you to be very honest and helpful in your comments as to what would be a good idea to change, what would be good things to keep the same, and I'm willing to bribe you in exchange for a good response rate. So here's my deal. There are 23 of you. If at least 21 of you complete a course evaluation through the university, every single one of you gets a point extra credit. So only 2 of you can let the class down. So I'm going with peer pressure here to help get my response rates up. And I can keep track of how many responses I have, but I don't know who's completed it. So next week I will send out a reminder to those who have not completed to urge them to do so. But I will make that deal with you now, 1 point extra credit for everybody for filling out the university's survey for course evaluations. It used to be the case that we got to add our own questions to the university course evaluation surveys, and they took that privilege away. So I am offering you an additional opportunity to complete a custom Qualtrics survey about this class. You will get an invitation to that tomorrow, And the way that it's set up is that within Qualtrics, I can tell which email address has completed a survey, but I cannot tell which survey is yours. So it is still anonymous. And if you complete a survey by the end of finals week, I will give you another point of extra credit for your time. So up to 2 points of extra credit for participating in the evaluation component of this class. I valued your comments and I value your time in providing them, so that's why I want to compensate you. How's that sound?
Great.
Good?
Yep.
All right, that's fair. So be on the lookout for that. Email scheduled to go out tomorrow morning, and like I said, you'll have until the end of finals week to work on that. The university's course evaluations close at the end of classes, so a little bit earlier than that. Let's see, I'm trying to think if there's any other updates. I put up new stuff last week for today, so we've got Lecture 6, Example 6A, and Example 6B for the last 2 weeks here of class, and that's it. We're almost there. I know it seems like you have a lot of work in front of you, but we're almost there. All right, any other questions or comments, things I can help with or clarify? No? Ready to do path models? Hooray! Path models are fun. And once you get the hang of it, not all that challenging. Easier than pancakes and crepes, dare I say. So away we go. The finale, as it were, multivariate models using path analysis. So this is the way in which I would address research questions involving multiple outcomes at the same time, potentially involving generalized linear models, and as well as research questions involving mediation. So anytime that you have a variable that is both a predictor and an outcome simultaneously, this is the optimal way to specify models for those sorts of outcomes. All right, here we go. No, not quite. There we go. So in terms of what is possible, one thing that you will find, especially if you look at older textbooks that cover path analysis, it's like a chapter in a book, or particularly within structural equation modeling books, a lot of them say things like path models assume multivariate normality. Path models in certain software assume multivariate normality. And once upon a time, that was your only option. But things have changed quickly and radically. I set a new personal record for example 6A that goes with this. I have 4 different programs that you can do path models in because it's a multivariate normal example. Unfortunately, that generalizability does not extend to all 4 programs once you add in link functions. So if you're willing to assume multivariate normality of your outcomes, then you can do path models in all different kinds of packages. So in SAS, there's something called proc-calis. In Stata, there is a package called SEM and GSEM, which I think stands for generalized in that context. There's Lavon and R, which honestly, I don't hate. It's the first R package I don't hate. It worked like it was supposed to, and the output was nicely formatted, and I knew what it meant. It was amazing. It's like, oh my God, I never knew that this is what R packages could be like. It brought me joy. So yeah, Lavon, not so bad. Lizrel was the very first program. It was written by Carl Jorskog around the time I was born. And it was so difficult to use that people who were able to use it got to be known as Lizrelites. Like it was a special cult of people who were able to do this. I heard this story from Susan Embretson, who was old enough to have been there. I have not used Lizrel. I took a workshop on it in grad school, and it's all gone. EQS is what I learned initially to do this with, and that program is somewhat dying as well. That's Peter Bentler's program. Amos is another package that is part of SPSS, but it's a separate add-on, and it has a nice diagram and less code, so people like it for that reason, but it's also less flexible. One thing to note about all of these different packages that you can do path models in, not a one of them uses denominator degrees of freedom, so that means that all of your hypothesis tests are going to be Z's for single parameters or chi-squares for multiple parameters. And none of them have REML as well. That's not on here, but I thought about that, even though in theory they could. So REML, residual maximum likelihood, is only available for conditional normal outcomes, but for whatever reason, software that is built for structural equation and path models does not include it. So regular flavor ML is what you have. Robust cases we'll talk about that later. There's a robust version that shows up in some of these packages too. Okay, I just heard something. What did I just hear? It sounded like a laugh track. Am I being funny and I don't know it? I usually know when I'm trying to be funny. I wouldn't have expected a laugh track. That would be a fun bonus. Anywho, software for not normal outcomes is a little bit trickier to come by. So it is possible. Stata's GSEM is one package that has quite a few different link functions and conditional distribution options. M+ is the one that I am most familiar with. Levon and R does ordinal outcomes only. So that's the bummer with it. And it only does limited information estimation for those ordinal outcomes, so we won't be able to use it for the last example, which is a path model that ends in logits. One catch with these sorts of packages, though, is that once you switch to something that's not normal for a conditional distribution, the only way that you can allow relationships between variables is through random effects or direct paths. So like you could have one outcome predict another, but you're not allowed to just let them covary. If there's no separately estimated residual variance, there's no separately estimable residual covariance within full information maximum likelihood. So I will show you what to do instead, and you can learn from a mistake that I made when I attempted to publish a path model once and did not understand this as well as I could have. All right. So any questions so far? Lots of words here. Okay. So path analysis software vary in their capability for maximum likelihood. So with multivariate normal outcomes, the difference between what is known as full information maximum likelihood and limited information maximum likelihood is the same thing. So the only difference is with respect to what happens to missing data. You end up with the same parameter estimates in theory if your data obey the assumption of missing at random. So the term full information, you will see this term used a lot. FIML is the acronym for that, FIML. And that means that it uses all of the original data to estimate the model. So all of the original response patterns, the raw data. And because it uses raw data, you are allowed to have missing information to some extent. Limited information is what is a general term that means the model is being estimated on a summary of the data instead of the raw data. So you can estimate path models by inputting a covariance matrix, for instance. You can give summary statistics about a set of variables, such as might be published in an article, and you can recreate their analyses. The problem with this is that you can't have missing data because each of the summaries doesn't know where it came from. Another distinction that you'll come across is the use of the term robust maximum likelihood. So this is a process that's described in Ender's chapter 5, is on your reading list. He has his book, Applied Missing Data, I think it is, Applied Missing Data Analysis. It's a really good book. And these chapters are on the reading list of every class that uses maximum likelihood because I like the way that he explains it very, very clearly. He has a new version of the book that's coming out this fall, I saw. But in general, as part of your output, when you invoke robust maximum likelihood, you get this additional statistic called a scaling factor. And it provides you with an approximation of how far off from multivariate normal your data actually are. And it uses that approximation to try and correct model fit statistics, which we'll talk about today, as well as standard errors for the parameters. So my approach when I'm doing path models, like in practice, is just to use robust maximum likelihood. Because if it's the case that your data actually are close enough to multivariate normal, it will estimate your scale factor as 1, and then it reduces to just regular flavor maximum likelihood. So there's nothing that necessarily is hurt by it. The corrections to the standard errors tend to work not well in really small samples, but if you're having a really small sample, you're probably not doing a path model in the first place. So you will get these scaling factors as part of your output. And robust standard errors can also be requested in some packages that do the same thing, but they don't adjust the fit statistics. So I'm going to try to use robust maximum likelihood when possible, but they're not all packages are capable of doing that in the presence of missing data. So I have a lot of words in here that summarize my searching through the documentation of various programs to figure out what they do. That way you don't have to. That's my ultimate goal here. So we're going to be using full information maximum likelihood, meaning that we're working with the original data so that we can have missing data to some extent. And we're going to be using a robust version. That way, if we have not quite multivariate normal outcomes, we can get something that is reasonably believable despite that. To do robust maximum likelihood ratio tests, the formula is a little bit more complicated. So rather than just taking the difference in -2 log likelihood, you have to also compute the difference scaling correction, which the ingredients for it is right here. And then once you have that, you can compare the difference in -2 log likelihood that's been rescaled to the chi-square distribution. So this process, I don't know that you're going to need to do for anything for this class, but I wanted you to have this. Here's a link to the M+ documentation that describes it. In my structural equation modeling class, I have a number of spreadsheets that I've built to do model comparisons where this formula is built into the spreadsheet. And also in R, there's an ANOVA function that seems to understand if you use robust maximum likelihood, and it does the proper correction for it. So the regular ANOVA function for comparing models can be used with this too as an R, that's what I've found. So just be aware that when we're in robust maximum likelihood, -2 log likelihood differences have to be done a special way. You can't just take the straight difference. All right, so enough caveats. Let's get to some pictures. Yay, pictures? Pictures and equations. So path models are pretty much universally described using the same drawing conventions. I don't know where they came from, but they've been in existence for decades. So you will see diagrams that look like this here on the bottom, as this is an example multivariate analysis, where things that are real are in boxes. So variables that you have observed in your data set are shown in boxes. Things that are not real, that are latent or unobserved, are shown in either circles or arrows. So this goes with latent factors in the context of SEM, which we're not going to do, but it also goes with things like error terms. So we don't know until the model is fit how much variability is left over in Y1, for instance, and so the idea that there's this residual that has an estimated variance is shown as a latent variable in this picture, like this. Question?
So in an IRT sense, would the boxes be observed scores?
Yes, they would.
Okay, and then the ovals would be the, like, theta?
Yep.
Okay.
Yep, theta would go in a circle or an oval, and item responses would go in the boxes.
Okay.
Yep. So boxes are for real things, circles are for pretend things. That's the rule. Excuse me, latent things, not pretend, but unobserved. Likewise, the arrows have special meaning. So an arrow that goes from a box to another box, this is a fixed slope. So this is a regression of x1 predicting y1, for instance. And I have labeled it with this coefficient here, beta x1, and then I'm using y1 as a superscript. This is one way that I've seen people try to notate path models, is to put what it's predicting as a superscript and then what the variable that is doing the predicting as a subscript. I'm trying that notation here. It works because the model's not that complicated. So this shows that x1 is predicting y1, x1 is also predicting y2, x2 is predicting both of these things. And so that's shown as the fixed effects here in the equation on the left. And then the two-headed arrow is a covariance. So this is the idea that y1 and y2, whatever's left of them after being predicted, gets to be related. So it's a residual covariance specifically if it's between two outcomes that have been predicted in the model. And an arrow that has two heads that's going into itself is sometimes used to denote a variance. So these are two different ways to show that y1 has a variance or y2 has a variance. A curved arrow is usually what's drawn here, but this was in PowerPoint, so that's curved arrows are a little bit trickier to come by. And yes, I do all my path model diagrams in PowerPoint still. I know there's fancy drawing software, and each of the path analysis programs will spit out a path diagram for you, but I tend to just do it myself because it's faster and I have more control. So this picture over here is meant to have all of this stuff if I were to write it out as a linear model. The only thing that's not in the picture are the intercepts. So we would expect that every variable that is an outcome would have an intercept in addition to whatever fixed slopes. And sometimes you'll see those put in a path diagram as a triangle. The triangle, I think, is stupid. It pisses me off. So I don't put triangles in my path diagrams because all variables should just have a mean, and that seems like something that should be obvious. So, and each of these, y1 has a separate estimated variance, y2 has a separate estimated variance, and they have a covariance. And so the unstructured R matrix that goes with this picture is right here. So this is the type of model that could be done using mixed, like your homework 5. I could stack y1 and y2 into one column, and I could have a separate column for x1 and a separate column for x2, and I could use dummy codes to set up this model. The reason that I could do this in mixed is that every variable in this story is either a predictor or an outcome, but not both. So y1 and y2 are outcomes, the end. They relate to each other via this covariance, but one's not predicting another. x1 and x2 are predictors of each of these two outcomes, the end. Okay, how are we doing so far? So when you go to write your path model, it will be written more or less like this. You will write out what predicts each variable with which predictors. We will list out, for the sake of completeness, all of the estimated parameters and label them, and we can do math on them. So within path analysis software, there's ways of doing linear combinations to get simple slopes out of interaction terms, unobserved group differences, that kind of thing. So, as I was saying, this is just a multivariate model right here. Why would we do it this way? One reason is to test differences in effect size. Another would be in the context of what I've referred to as actor-partner models. So for dyadic data, for instance, we might have person 1 and person 2, and the paths going from x1 to y1 or x2 to y2 in that context would be called actor paths, and these cross paths would be called partner effects. And so we can test whether or not my predictor has a bigger impact on my outcome than your outcome, or vice versa, any kind of comparison of slopes like that. Another reason we would choose a path model over just a regular multivariate analysis in univariate software is to do mediation or indirect effects. So that will be part of this unit as well. Okay, how are we doing? So far, just some pictures to go with ideas that you already have. In path analysis software, and this is true in regression to some extent, although it sort of falls by the wayside in this class because of the generalized focus. There are two different types of solutions that you can ask for. One is unstandardized, which is the one that we're used to seeing, and the other is standardized. So if we have the solution for the fixed effects in the metrics of the original variables, so like just what shows up by default in your output, that's called unstandardized. And this would be useful to you in most cases. The parameters are going to directly try to recreate the variables' means, variances, and covariances that are involved. The alternative is a standardized solution. And so back when you initially learned regression, if you learned standardized regression coefficients, like standardized slopes, that's what this is, this version. So this type of solution is instead trying to reproduce the variable's correlation matrix, assuming all the means are 0 and all the standard deviations are 1 for the total variable. So standardized solutions tend to be reported in the pictures because then you can directly see on the same scale how strong each of the effects are from the predictors to the outcomes. So they're useful, standardized solution is useful within a solution to see which variable is relatively more important. However, a big caveat to interpreting what they mean is something that I only recently learned more about because I just sort of accepted this at face value for years, but it turns out that standardized slopes are not actually standardized. I know. Here's the thing. The way that I was taught to interpret a standardized slope is it's the change in y for a 1 unit change in x, which would be a standard deviation of x, right? Does that sound right? Here's the thing, though. To the extent that the multiple predictors of the same outcome are correlated, what's relevant is not the predictor's total variance, but their unique variance, because the slope represents the predictor's unique influence on the outcome after controlling for all the other predictors. So really what should be standardized is not the total variance, but the amount of the variance that's going into the prediction specifically, its unique variance. And it turns out that if you take the original, if you correct for this, replace this with the unique variance and multiply it by the same unstandardized coefficient, the result is the semi-partial correlation instead as an effect size. So it is the case that standardized slopes can go out of bounds. They can go above 1 or below -1 because they're not really standardized for the part that shows up in the model. They're only standardized for their original. And of course, this falls apart when you don't have multivariate normal land. So standardized coefficients for generalized linear models are squishy at best, even though some programs will report them. So I tend to be less of a fan of this than I used to be because of this limitation. But they're still very common, and they're easy to ask for. So I want you to have access to them. I would say a complete reporting of any results of a path model would have an unstandardized solution, all the standard errors that go with it, and then potentially a standardized effect as well, so that your reader has all the original information to work with in terms of what means what. All right. It just gets worse. There's so many new words in this unit. Yes, sir.
So, going back to when we were doing ordinal regression, would there be any drawbacks to doing a multivariate regression as opposed to ordinal regression?
Well, you can do a multivariate ordinal regression where you're predicting several ordinal things at the same time. Is that what you mean?
Well, like instead of having like 5 different submodels for like 1 to 5, seeing like how they all simultaneously affect the outcome. Would that not make any sense at all?
It might make sense. Are you thinking of like making the submodels separate outcomes explicitly? Is that what you mean?
Yeah, I'm like instead of doing like 5 different models, just like trying to put it all into one thing, I guess.
If you have one ordinal outcome, from this perspective, it is still one box.
Okay. Like if you wanted to do like Likert scale responses predicting passing a class.
So if you want it to be a predictor instead, that is a different story.
Okay.
Because then you have to make a choice as to whether you want to fit a linear effect of that ordinal predictor, which means the change on the outcome from going from 1 to 2 is the same as going from 2 to 3, 3 to 4, 4 to 5. That's a testable assumption.
Okay.
So the most parsimonious version of the model would be a linear effect of an ordinal predictor. The most realistic version of the model would be to let every separate increment have a different slope.
Okay.
So like a sequential type of coding scheme where the change from 1 to 2 has one effect, the change from 2 to 3 has another, 3 to 4 has another. And if all of those incremental sequential slopes are the same, that reduces to just linear.
Okay.
But if they don't, then you probably shouldn't just draw a line through them all and call it good.
Okay. So like a multivariate path model would not add, like it wouldn't make it any better. I think maybe since we're just like this is new stuff, I might be mixing stuff up, but like I don't know, the picture just like it makes a lot more sense.
You like the pictures?
Yeah,
I
like
pictures.
being able to demonstrate it that way as opposed to like having all these different submodels.
So if Y1 were ordinal in this picture, you still have your submodels. You would still have
So it'd just be like one box, you know, and it would be 5 different path models.
Not in the software.
Okay.
No, you would still just request one slope from X1 because an ordinal model is a proportional odds model where the slopes are equal across the submodels. And you would tell the program that this is ordinal and it would create as many intercepts or thresholds as you have submodels. It figures out how many categories there are and it gives you those.
Okay.
So like from that perspective, it's treated as if it's just a regular outcome because the only way the submodels differ from each other is in their intercepts.
Okay.
And they just get printed.
So you have like a ton of triangles if you were.
Yeah, you'd have to have a lot of triangles or a very complex system to denote that.
I just like visual stuff better than.
A lot of people do. You're in good company. And I will tell you, your 6th homework, the very last one, not quite ready yet because you have enough to do this week. Am I right? See, that was sort of a joke, but kind of not a joke, right? Because it's only Tuesday. Like, I was like, is it only garbage day today? How is that possible? It feels like it's at least Thursday. But no, it's only garbage day. Point being, where I was going with this, when I have to do a very complicated path model, I draw it out first, and then I write the equations from the picture. And for your last homework, that is what I would recommend. Read through the instructions and draw yourself a picture, and then write your equations. And when people try to explain what they want to me, this is what's happening in my head as people are talking,
I
usually.
think my question would make more sense if there was multiple outcomes. I think that's where I'm.
Well, there's two
There's
here.
still only one outcome.
There's 2 outcomes here.
No, I'm saying like in the Likert versus like. I think I understand what I'm saying now.
If you wanted to have separate slopes across submodels, you would be better off saying it's nominal rather than ordinal.
Okay.
I don't know of a way within traditional path analysis software to hack it into a non-proportional odds model.
Okay.
I don't know how that would work. Not to say it can't be done, but I've never been able to figure that out. Okay. Other questions, thoughts? All right. So different solutions. Okay, more words. So this is confusing. I'm just going to put it out there. But I feel like it's something that's misunderstood because it's confusing, so I'm making a point of describing traditional terminology and how you can reconcile that with what it means across different packages. So if you read your path analysis textbooks, you will see them use the terms exogenous and endogenous. Are these words that you've heard before to describe variables? Maybe? So I had to come up with mnemonics to keep track of which is which. And so my mnemonic is that exogenous is like exogenous, meaning these are predictors, because in my notation, X is always a predictor. And endogenous means endogenous, meaning there's an arrow going into it because it's an outcome. So exogenous variables are predictors, endogenous variables are outcomes. So in this example model here, I have 2 exogenous variables, x1 and x2, and 2 endogenous variables, y1 and y2. And it's very clear cut here because each variable is only playing one role. Or you could have something like this. So I've changed the path from y1 to y2 to, rather than being a residual covariance, now it's a direct path. So this is an instance of a type of model that you could not do by tricking univariate software without going to additional trouble with respect to the R matrix and say, it would not be worth the additional trouble, let's put it that way. Y1 is now a predictor of Y2, so Y1 is a predictor, but it's also an outcome of X1 and X2. It's doing both at the same time. So this is one way, if Y1 and Y2 did not have conditional normal distributions, that you could put in the analog of a residual covariance between them is to change it to be a direct path. So now there is a relationship between these 2 variables, but it changes the story though, because now the relationship of x1 to y2 and x2 to y2 is being controlled for y1, which may not be necessarily what you want. So each of these paths from a predictor box to an outcome box still represents a unique effect, the same as in any linear model. So this changes the definition of what they mean in the second picture relative to the first, because now x1 and x2 are being controlled for y1 in how they predict y2, and up above they're not. So y1 is still considered an endogenous variable because it's being predicted by x1 and x2, even though with respect to y2, I would call it a predictor. And any variable that is being predicted will automatically have a residual variance estimated for it, as well as an intercept. Those are things that just show up in the packages, although I like to write all the parameters so that I know what's what. Okay. So then what happens in the context of missing data ruins this nice, clean distinction. So endogenous variables, if it's an outcome, gets an intercept, a residual variance, and you can ask for residual covariances if you're in multivariate normal land. With respect to missing data, though, exogenous predictors cannot have it. So in M+, and in our Levon, so according to Jonathan, this has changed since earlier versions. The current version that I was using to build this example behaves like M+ does. In this sort of path diagram here, x1 and x2 cannot have missing data. Cases with missing data will get dropped because they are exogenous predictors, the same as in any linear model. The reason for that is that you can't compute the predicted outcome for each person without knowing what their predictors are. So this is a conditional log likelihood for each outcome. It's conditional on the predictors. And so we can't work with cases that don't have all of the information that go into the likelihood calculation. But the good news is that exogenous predictors also don't have assumed distributions. So from this perspective, it's the same as what we're used to in any linear model. You can't have cases that are missing predictors, and you don't have to assume anything about your predictors. They can be whatever distribution, whatever type you want. Categories, continuous, semi-continuous, whatever you have. So how it gets fixed then is where the confusion comes in. So a lot of people are confused when they first learn this, that cases with missing predictors get deleted in path models and in structural equation models, the same as in any linear model. No, it's only the outcomes that can have incomplete data. So the data structure that's going in here is the same wide data structure we started with, where each person is a row of data. So they have separate columns for their predictors and their outcomes. And the rule is you can only have missing data on an outcome, not a predictor. You can add other variables into the model, though, that are supposed to help with missing at random as an assumption. And there's an option to do this in some of the programs. But there is a workaround that you can use to have data that are missing on predictors, which is to change them from being exogenous to endogenous with respect to the program. So you can trick Levon and M+ into thinking a predictor is an outcome by asking it to estimate the predictor's mean, variance, or covariance with something else. Then from the program's perspective, even if that variable is not being predicted, it's endogenous. Its parameters are then part of the likelihood, which means you can have missing data. And this is what proc-calis does if you invoke full information missing, full information maximum likelihood. And it's also what happens in Stata's SEM package if you do that. It automatically brings all the predictors into the likelihood and makes them endogenous, even if they're still predictors in the context of your model. So this is why it's really confusing, is because you can have predictors that are endogenous or not, depending on your software. So that label doesn't really help. So this is the, like I said, I have a lot of words on here to remind myself what all the packages are doing after looking through all their documentation. So if you invoke full information maximum likelihood, which is supposed to handle missing data, in proc-calis and in Stata's SEM, it brings all the predictors into the likelihood and treats them as endogenous. That's good in that you can have missing data on them, but it's bad because then they're assumed multivariate normal. And that may not be true. So here's what I'm going to say to try and make this less crazy. Ask yourself, is the variable in the likelihood? It's either there without your permission, it just happens, if you're in SAS Calis or Stata Sim. It is in the likelihood if you bring it in, if you're using M+ or R. If it's in the likelihood, that means that the program is responsible for estimating its mean, its variance, and its covariance with other things. That means that you can have missing data on it, but you have distributional assumptions at the same time. If it's not in the likelihood, then it's a predictor. It's truly exogenous, and you can't have missing data, but there's no distributional assumptions. So I would avoid bringing predictors into the likelihood unless you have a reasonable expectation that they would be relatively normally distributed, and there's enough missing data to where it matters. Otherwise, I would probably do something else like multiple imputation. So in the example 6a, I have an example of what this would look like to bring a predictor into the likelihood so that you can have missing data on it. So super confusing. Not my fault though, I swear. I'm just the messenger here. Okay, yeah. It gets better from here. I swear. You look like you don't believe me. It does, it gets better. Okay, identification and fit then. One of the things that we haven't worried up to this point, but we get to start worrying about now, is the idea of whether or not we can actually estimate the model we specified, and do we have enough information to do so. So identification is the term that is used for basically, is this thing going to work? Have you asked more than the data, from the data than what is logically possible given the data you have? If not, it should be identified. In path models, we're not worried about latent variables. There's a whole nother layer of identification that goes with those. So we can skip that part for now, but we'll spend a lot of time on that in SEM. In path models, we are worried about fit with respect to how well the model has captured the relationships among the variables. And in order for fit to be testable, we have to have estimated fewer parameters than what is logically possible. So calculating how many things you can possibly estimate is referring to model degrees of freedom and total degrees of freedom for possible. So this has nothing to do with people. So up to this point, I have known of two kinds of degrees of freedom. There's numerator, which is like the number of slopes in a test, and there's denominator, which is a function of the number of people in your sample minus the number of fixed effects you spent. This is neither of those. This is yet a third type of degrees of freedom. It refers to your summary statistics, essentially, of the data that you're going to be analyzing. So if we say that we're focusing on all of the variables in a problem as being in the likelihood treated as outcomes, then total degrees of freedom is found by this formula right here. It's the number of variables times number of variables plus 1 divided by 2. That part gives you the total number of variances and covariances among the variables at hand. Then plus v puts back the number of means. So if I have 4 outcomes, then there are 14 pieces of information that I have to work with to estimate my model. I have 4 variances, I have 6 covariances, and I have 4 means. That's degrees of freedom. The question is, how many of those do I need to spend to get an accurate representation of the relationships in my data? So model degrees of freedom then are the difference between the number possible and what you spent. And this number needs to be positive in order for model fit to even be a problem to worry about. So in terms of what goes in and what comes back out, every outcome has a mean, every outcome has a variance. What is being estimated to recreate them is an intercept per outcome. So quick review here, what's the difference between a mean and an intercept? Like in a standard linear model.
Intercept is when
All the predictors have to be 0.
Yeah, when all the predictors are 0, it's a conditional mean. The mean is just the mean, like the marginal mean. So as long as each outcome gets an intercept estimated, that intercept will recreate in linear combination with the predictors the actual mean of the data. Likewise, every variable starts with a variance. After it's predicted, we will get a separately estimated residual variance for each outcome that will perfectly recreate the observed variance. So these are usually a one-to-one correspondence, something that you do not have to worry about as being responsible for any problems of fit in your model. So long as each variable starts out with a mean and a variance, and it has an intercept and a residual variance coming back out of it, you're fine. I will note, though, that what you get on your output in M+ depends on whether or not the variable is actually being predicted. If you bring a predictor into the likelihood and you don't predict it with anything, its parameters will be labeled as mean and variance as opposed to intercept and residual variance. But they mean, because they're unconditional in that case. Here's where the problem can come in. What's going in as input to this process is the observed covariance between every pair of outcomes, as well as the observed covariance with each predictor and each outcome. Covariances among predictors are not part of the story because they're not in the likelihood. So we have a choice then of how we would represent a relationship between two variables. We can set it up as what's known as a path. That's a slope. So like a regular regression fixed slope is now called a path. And sometimes a direct effect. Those are synonyms. So go back to my picture here. Yep. These directed arrows going from the x's to the y's, these are known as direct effects or paths. They are just your slopes. They just get special names in this context. So I can put one of those in to describe the relationship between two variables, or I can put in a residual covariance. I can just let them be related. And that's an interpretational choice as to what I want to know. Do I want to know what the predictor's unique relationship is in predicting an outcome, or do I just want to know how two variables are related after controlling for some other stuff? So if we leave out these specific pairwise relationships, that's where there's room for potential misfit of the model. If you leave something out, you're assuming it's 0, just like you would normally do if you leave out a slope of the model. So there are words that go along with this idea as to whether or not we've left something out and have to worry about fit. So assuming that our model is estimable, do we have enough information to actually get the estimates back? And the three scenarios here are under-identified, just-identified, and over-identified. Under-identified means you cannot do this. You are trying to estimate more parameters than pieces of information you have with which to estimate them. It's like being overdrawn at your bank account. You've spent more money than you have. So you would have negative degrees of freedom. I have pictures for these things here in just a second. Just identified for path models, I would say is generally where you want to be. Just identified means that you have put in something for every single pair of relationships, pair of variables, and so you're not going to be wrong. You've covered all your bases. You've spent all your degrees of freedom. So then the question is just about how useful are the slopes? How strong are their effect sizes? How good is this model at predicting these outcomes? And you don't have to worry about misfit as a potential problem in interpreting your results. Over-identified is when you have degrees of freedom to spare. You've left stuff out because you can, because those relationships are already described. I had a mnemonic the last time that I taught this class someone gave me. For over-identified is like overlooked. Like if you've overlooked certain pairs of things, then it's over-identified. You haven't spent all your degrees of freedom. And this is the situation in which you have to demonstrate that that choice to overlook certain paths is not a problem. So the idea of checking fit is to make sure that anything you've left out really doesn't need to be there. Otherwise, the rest of the relationships can be biased as a result. So here's some pictures. So let's say that I've got 3 variables here. I have x1 predicts y1, which predicts y2, or y2 predicts y1, which predicts x1. Both of these models have 3 variables. Given 3 variables, there's 3 possible means. So if I give each variable either a mean or an intercept, I'm good. Given 3 variables, there's 3 possible variances. As long as I give each one either a variance or a residual variance, I'm good. There are 3 possible covariances, and I've got 2 paths in here. I don't have anything that directly connects x1 to y2. So this is an example of an over-identified model. I've overlooked one of the paths, so I have 1 degree of freedom left. That's like saying that after I predict y1 from x1 and predict y2 from y1, that there is no remaining relationship between x1 and y2. So the relationship between x1 and y2 is exclusively carried through y1 here. What the model says is that the relationship between x1 and y2 is this path times that one. There's a whole set of very complicated rules that we're not going to get to today. But the logic of it is that all of the relationships are already taken care of by the paths that are in the model. That's the idea. So the model is saying there is a relationship between x1 and y2, but what it is governed by these 2 paths that are here. So there's a chance to be wrong. Now what about the bottom one? This is, believe it or not, statistically equivalent, even though it means something very, very different. Here you're saying, no. y2 predicts y1, which in turn predicts x1. And math don't care, folks. That's one of our favorite sayings around our house. Math don't care. Math don't care which of these theoretical orientations you prefer. These are going to fit the same. They will make the same predictions and they'll have the same degree of fit, because both of them are missing a direct relationship between y2 and x1. Can I tell you a quick story? In one of my previous jobs, that narrows it down a little bit, I was at a dissertation defense with someone who had a very complicated structural equation model, but the part that was of most interest among the latent variables basically boiled down to this problem. And there was a committee member who thought they knew more about methods than they did, as evidenced by the fact that this person wanted to argue with the student as to whether they got the arrows going the right way. They wanted to argue that the middle box should be here and the first box should be there, and did they try it that way and see if it fit better? And I was sitting there, I didn't have a mask on because, we didn't have a pandemic then, but I was sitting there like covering my mouth, like trying not to laugh, like, come on, student, you got this. And this student was one of those people who was very deferential, like they weren't very sure of themselves and they didn't want to like correct a faculty member. And they're like, maybe I'll try that and I'll get back to you. And I'm like, nope. This is the same. And this is why, friends, that you cannot say without rolling your eyes that path models and structural equation models are causal modeling. There will be no causal. What this is a reconstruction of a covariance matrix of things that were all collected at the same time. There is no way mathematically to say which came first and which way the arrow should go. The only way that you can talk about causal anything is to have a design that supports causal interpretability. So random assignment as one option. Quasi-experimental settings with the appropriate controls and whatnot. But it all comes from design, not models. So this is not causal modeling. Now, there was one time in my life that I got to argue against reviewer 2 that the arrows were going the proper way, and I was absolutely sure I was right. 1 second. Do you know why? Because Y2 was collected 5 years later. And I was like, I'm pretty sure that the past has to stay in the past, and the future is the future. So I'm also pretty sure that this thing that happened 5 years later did not cause the thing that happened before it. And that was the one time I was like, I feel like I'm on solid ground here with the arrows going the way they are, because time, the space-time continuum. Okay, question?
So putting this into words, could we say like, if X1, let's say X1 is a study that we conduct and Y2 is publication, then Y1 could be like, is your p-value less than 0.05? Because then if you go reverse, like, oh, is this published? Well, is your p-value less than 0.05? Well, then you probably don't have a study.
Yeah, there's
I'm
a
trying to be
conditional.
a little sarcastic too.
Yeah, there's a conditional logic thing here, and there's certain combinations that, arguably don't make sense. Like, for instance, if I had demographic variables like age, I'm not going to put age at the end of the chain here. Nothing causes age. The unit that causes age, the calendar. Like having a demographic characteristic as the end of a chain does not make any sense conceptually, even though mathematically there's no problem with it. So this one over here, by the way, is a non-equivalent model, because this one just has covariances between the variables. It doesn't have a direct covariance between the two, and so this is actually saying there is no relationship between X1 and Y2 at all, because covariances work differently with respect to how they predict the other model-implied relationships. So this one is indeed different. This is a much different statement.
It kind of reminds me of chemistry a little bit,
Probably.
like reversible reactions and all that stuff.
Yeah. Here's just identified. So here's 3 different versions of a just identified model. You got 3 relationships, 3 things in the model form. Bases covered. You spent all your money, basically, but you can't be wrong. So there are direct relationships between each pair of variables here, as well as direct covariances on this side. So this is degrees of freedom equals 0, meaning that fit is irrelevant because it has to be perfect. There's no place in the model that you have overlooked something that could possibly be needed. And then you get into something like this. This is an example of under-identified. So there are 2 paths here, but there's only 1 covariance that you would have to estimate them. And you can't pull 2 things out of 1 number. So that won't work either. So in path models, unless you try to do something crazy, you're probably not going to end up with under-identified. But if you try to put the same type of relationship, 2 different relationships between 1 pair of variables, that would be the one way you could do it. All right. 142, how are we doing? Yeah. Thumbs sideways is my only goal for right now, by the way. This is the rating system in my other class. We have thumbs up, we have thumbs sideways, and thumbs down. At this point, the best I'm hoping for is sideways, because it's a whole lot of abstract concepts and words at this point. Like word salad. Need some ranch dressing for this shit. Anywho. Okay, questions before we call it a day? Please. This one? This one and this one? Up. This and this. Okay. So these are 2. So Y1 would be a mediator in the direct arrows case, whereas Y1 is just correlated in these, because the 2-headed arrow signifies a covariance that's undirectional. So they're just letting them be related. So the model in this case does not imply a relationship between X1 and Y2, whereas it does through these paths right here. Yes, Y1 is a mediator in either of these chains. and it will fit the same, because both of these models do predict a relationship from x1 to y2 that goes through here. And so this is where we get into some of the terminology. One arrow right here, this is a slope. It's known as a path or a direct effect, as opposed to an indirect effect, which is the multiplication of two slopes. So if I multiply this slope times that slope right here, that is called an indirect effect. And we will have the software do that for us, of course, but not today. Okay.
The red one only indicates the correlation.
Yeah, the two-headed arrow indicates a covariance, yes, in the unstandardized solution, and its correlation in the standardized solution, yes. So this is omitting a path, but it changes the prediction of what's going on because of the types of relationships that are included.
I don't know if this is helpful, but it kind of reminds me of like a subway system. Like if you want to get from point x1 to point y2, you got to go through point y1. And then like in the middle column or the middle row, x1 to y2 is like an express train, if you can think of it that way.
Okay, I like it.
Yeah.
Yeah.
You just bypass y1 altogether.
Yeah. Yeah, Y1 would be like a hub. Like this is Atlanta or something. And there's no, you have to go fly through Atlanta if you want to go anywhere on the East Coast. But anywho, all right, 1:45. Time to go. Thank you for being here. See you Thursday. Let me know if you need anything. Bye, folks.
I was helping someone with their